Everybody, we are going to solve here in this video exercise number 4 of handout 1. So in this exercise they say that there is a system called S1. A system called S1, and S1 is defined by the following relationship between the input and the output. Xn equals the summatory from k equal minus infinite to n of xdk. Okay, so it tells us that you have to sum over all the values from minus infinite up to the point n where the signal is. This is the output of the system. And they say that we are going to make a new system putting two of those S1 systems in series. So we put S1, and in the output of S1 we put another S1. So, and then we get the output, the final output that they call sit n, and the input of the first system they call it xn, and they define the system S2 as just putting these two systems in series. So in the first part of the problem, they ask us to demonstrate the following: that is2 is LTI, and then they ask us to see if it is causal and or stable. Okay, so let's go ahead. So first of all, what you can see is that is2 is a series combination of two identical systems, S1. So if S1 is LTI, then for sure S2 will be LTI, because when you put together, when you concatenate or you put in series two LTI systems, then the overall system is an LTI. So basically, if we are able to demonstrate if S1 is LTI, if we demonstrate that one, then directly, basically, S2 will be LTI. Again, because both of them, S2 is made out of two ST1s in series. Okay, so let's check if S1 is linear. Okay, so very easy. So a system is linear when you input a signal x1 dn, and then you get an output iy dn. And if you have another input x2 dm, that creates an output i2 dn. So the system is linear if you make a combination of those two inputs, x1 and x2, a linear combination, and the output of this linear combination is exactly the output, the linear combination of the output. So it's alpha y1 plus beta y2 dn. So if I made a combination and I get the same exact linear combination of the output, then the system is linear. So let's go ahead and let's do that. So if we input into the system the linear combination, so if we put into the system the linear combination, sorry, this is x, of the inputs, what we do is we apply the definition. So the output is just the summatory from k equal minus infinite to n of whatever is in the input, which in this case is the linear combination. Okay, And in this case, we can separate this that way. This is alpha summatory x1 plus beta summatory x2. Okay, and by definition, this is alpha I1 plus beta I2, which exactly is what we were looking for. So yes, the system is linear. Sorry. Okay, let's check now if it is invariant. When the system is invariant, so very easy. If we have an input, which is xy dn, and because of this input, we get an output, which is y1 dn, which again we know it's the summatory of from k equal minus infinite to n of x1 decay of k. Okay, let's go ahead and see what happens. Let's move the page a little bit downwards. So let's see what happens if now we make a temporal displacement x1 of n minus n0. So if the system is invariant, then this has to be exactly the same output, displaced the same amount. If it is not, then the system is not linearly invariant. Okay, so let's calculate this. This is the summatory from k equal minus infinite to n, but in this case n is n minus n0 of x1 decay of k, let's say. And this is, by definition, exactly, this is exactly y1 of n minus n0. Okay? So basically that's the demonstration. Yes, is invariant. Okay? So again, as S2 is made out of two S1 in series, and S1 is linear and time invariant, then the solution is S2, yes, is an LTI system. Okay? Now they ask us to calculate if the system is causal and stable. And what we will do is we will solve this, but using, instead of the definition, using the properties of the impulse response of the systems, of the system of HDN, because typically this is much simpler to do. So let's go ahead and do the second part, where they ask us to calculate the impulse response of the system, so h to the n. And again, when we have h to the n, we will be able to easily calculate the if the system is causal and stable. Okay, so h to the n, per definition, is to S1 in series, so basically is h1 dn convolve with h1 dn. Two systems in series, the overall impulse response is the convolution of the impulse responses. Okay, so what is h1 dn? So h1 dn is the impulse response of the first system to the delta. So we put in the input the delta and we see the output, and this is the input response. So basically this will be the summatory from k equal minus infinite to n of the input, but in this case, as we are working out the impulse response, the input is delta Tn. Okay, so this is basically a series of delta, is delta in minus infinite, blah, 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 all the way up to delta in n minus 1 plus delta dn. Okay, this is basically it. Okay, So in this case, what will be basically H1dn? So that's very easy to calculate. It's very easy to calculate. So basically, let's imagine that we plot the following thing. In a k-axis, we plot delta of k. So this will be 1, this will be in 0 a 1, and basically everywhere we will have 0. 0, 0, this is delta of k, okay? So let's imagine that we have an n to calculate delta h1dn, delta dn, okay? So we can have two cases, that n is over here, so that n is negative, or that we have an n over here, which is an n positive, okay? So basically, h1dn in this case, let's take the case n is negative. So in this case, h1dn, again by definition, is the summatory, sorry, this is a k, there is a typo here, this is a k, and this k is what I have plotted over here. So this is the summatory from k minus infinite up to n of delta k. But in this case, n is negative. So we are exactly in this case. So if n is negative, and what I have to do is make the summatory all the way from minus infinite to n, what am I summing? I am summing zeros everywhere. So basically this is 0. And what happens if n is more than 0 or equal than 0? Then in this case, h1dn will be the summatory of from k minus infinite to n, the same n, of delta k. But in this case, we are here. We are in a point which is positive. So the summatory of all the values of delta k from minus infinite up to the n that I am calculating is always adding 1. So this is 1. So basically what are we having here? We're having a signal that is 0 everywhere in the negative values and 1 from 0 to the positive values. This is exactly the definition of udn. So h1dn is exactly udn. Okay, so let's move a little bit forward, because what we need to calculate is we need to calculate h2dn. Okay, and h2dn is basically h1 applied to h1 of the input signal. Okay, so h1 we know is the summatory from k equal to minus infinite to n of whatever is inside, but in this case inside we have h1 of k. And in this case, sorry, this is k here, and in this case we know that h1 is udn, so this will be u of k from k minus infinite to n. Okay, what is it? So this is u in minus infinite plus all the way up to u on n minus 1 plus udn. Okay, so what is this? What is this? Look at that. We can draw or we can calculate. Okay, we are having here a signal that we have to add udn. Let's begin from the end. udn we know is this. Bum, 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 bum. But we have to make the summatory, or we have to add to udn u of n minus 1. You know, u n minus 1 is over here. It starts in 1. So if we add another udn here, basically we will be, this was in 1, we will be in 2. and all the same will be adding 2, 2, 2. Okay, and now we add another u in n minus 2. So basically we will have a 3 here, a 3, and you can see the pattern. You will have a 4 here and a 5. So basically what we will have is this ramp function here. Okay, this ramp function. So h2 the n is a ramp function, which basically is n plus 1 of u the n. So for n equal to 0, we have u the n. Okay, from n, or you can have the signal n plus 1 beginning on n equal to 0. So n plus 1 values 1 for n equal to 0. It has a value of 2 for n equal to 2, a 3 for n equal to 3, and all the way up here. Okay, so this is like a ramp function. This is the ramp function that we know, but displays to the left 1 unit. Okay, this is h2. So now that we have h2, we are in a good position to calculate. Let's add another page. Changing the color, sorry. I'm going to change the color of the page. It should be white here. Okay, so now we are in a good position to calculate if the system, if H2 is causal or not causal. Okay, so basically the definition of the causal system when you use the impulse response is the following. H2 is causal when H2 the n equals to 0 for negative n. Okay, and if you take a look at the ramp that we got from the previous point, you can see that H2 the n is 0 for all the negative n. So the system is causal. Okay, so the system will only react to whatever happens in the future. Sorry, in the past, whatever has passed in the past. What still hasn't happened, which are all these points that move into time into this way, they don't know. So the system is causal. Okay. Is the system stable? So when you have the HDN to see if the system is stable, basically you have to make the following summatory. So the summatory from n minus infinite to plus infinite of the absolute value of h2 the n. If this value is less than infinite, then the system is stable. If it is not, if it is infinite, basically it will not be stable. So in our case, the summatory will be of the absolute value of m plus 1 multiplied by u the n from n minus infinite to plus infinite. Okay. And this basically is, if you calculate, this is the area, is summing all these values. This is the summatory from 0 to infinite of all the values of the signal, which is n plus 1. So basically I have used u the n to change this limit from minus infinite to 0, and basically this tends to infinite. So the system is not stable. Okay, so let's keep moving forward. In the C section of the exercise, they ask us to obtain the relationship between the input x and the output zeta of the system S2. So we have to use to understand which is zeta n when the input is x the n. Okay, so that's very easy. Is we apply just the definition that we just got. Zeta n is the summatory from k equal to minus infinity to n of what we got between the systems, which is y decay. So remember that we have both systems connected in series. The signal here is y, the input here is x, and now the output we call zeta. So basically we are watching the output of the system at this point. Zeta equals y decay, the summatory, and basically y is doing the same but now with x. So there is a double summatory here. So it's a summatory from k equal minus infinite to n of what? Of y decay, and y decay is the summatory. We use another name like m, for example, just not to be confused, from minus infinite to k of x dm. Okay, so pay attention. Why have I used here the name k? Because basically this is what needs to be then sum over here for the definition of my system. So my system uses the name of the summatory that is able to go through the variable y. So here what I need is to have inside the result that depends on k, and this is why I put a k over here. And for the same reason that for I put an m over here, I put an m over here. By the way, these variables k and m, that basically you can change the name and call them whatever you like, are called dummy variables or dummy indices, because basically the name of the index itself doesn't play a role on the final result of the system. Okay, so this is just the relationship that they were asking for. Let's go to the D. Indeed, they say that we have to demonstrate that the inverse system to S2 is defined by the following relationship. So S2 minus 1 basically is defined by the following relationship. Xdn, which in this case is the input, equals to zeta dn minus 2 zeta d of n minus 1 plus zeta of n minus 2. Okay? We have to demonstrate that this relationship is the relationship of the inverse system of S2. Okay? How do we demonstrate that? Well, basically, if we call S2 the impulse response of S2 inverse H2 minus 1 dn, then by definition, if we put together in series H2 dn in series with its inverse, and putting in series means that I make the convolution of them, basically this has to be delta. This is the definition of an inverse system. I put the system itself in series with the inverse of the system and I got the delta. So I have to demonstrate that I put this function, I made a convolution with this function, and I will get a delta. Let's go ahead and let's see if this is true or not. Okay, so let's go. H2 convolve with H2 minus 1. What is that? Okay, I need H2 minus 1, and I don't have H2 minus 1. What I have is an input-output relationship for H2 minus 1. I need the impulse response of H2 minus 1. Very easy. So what I do is I put as x1 delta n in this equation, and what I will get is as zeta n will be H2 minus 1 of n for definition. Okay, so let's do that. In this case will be I put that over there. So sorry, in this case, is the input. I put as the input zeta then, and I get as, I put as the input zeta of n and delta, and then what I get in the output, which in this case is xdn, is h2 minus 1. Okay, so in this case we do exactly that. So we can, just to clarify this here, so if this is the inverse system, so this is h2 minus 1, what I do is input, in this case, a zeta, and then what I get is the x by this relationship, and in this case what I input is a delta, and here I will get as an output the relationship h2 minus 1. This is exactly, okay? Okay, so let's go ahead. If I go to this equation over here, I will have xdn is h2 minus 1 equals 2, and then zeta n is delta, so delta n minus 2 times delta n minus 1 plus delta of n minus 2. This is h2 minus 1. Easy. I input a delta, and what I get in the output is the impulse response of the system. I put in the system as xdn, the output of the system xdn will be h2 minus 1, and zeta is the input, in this case delta, and then applying the definition of the delta, I get this result over here. Okay, so now we are all set. h2 convolve with h2 minus 1. What is that? Okay, h2 we know it's n plus 1 udn, convolve with delta n minus 2 times delta n minus 1 plus delta n minus 2. And we operate over here. So basically, n plus 1 udn convolve with delta. What happens when we convolve with the delta? When you have to bring the delta where the function where the delta was. As the delta basically was displaced to 0, is basically the same function. So here we have n plus 1 udn. Then this convolve with that, it will be minus 2, and then the function displaced to 1. So n minus 1 plus 1 of u in n minus 1, and the last term will be displaced on minus 2. So this will be plus n plus 1 minus 2 on u multiplied by u on n minus 2. Okay? So basically we just operate. This is n plus 1 udn minus 2 multiplied by n u n minus 1 plus n minus 1 u n minus 2. Okay? And here we play a trick how we can further simplify that. And basically what we are going to do is we are going to, as we have to demonstrate that this is the delta, then we try to put some aware deltas in this expression. How we do that? Very easily. Look, you can see this is a trick that you will learn forever. The first term, we leave it as it is, n plus 1 udn. And then the second term is minus 2n. And what we do now is we express u of n minus 1 in the following way. U of n minus 1 is basically udn minus delta n. So if I take u the n, imagine the Heaviside step going to the right, and you take out the first value in 0, which is the delta, what you get is a Heaviside step displaced to the right on 1 unit. So this is true. Draw it and you will see that u of n minus 1 can be expressed as u the n minus delta the n. And here we do exactly the same. We put n minus 1, and we put u of n minus 2 in a way of deltas. Okay, think about that. How can we put this using the deltas? So this is u the n. I take out the delta or the value in 0, and I also take out the value in 1. And this is a u the n displaced 2 rights to the left. Okay? So now if we calculate all this, you can see that this is u the n. We take a common factor u the n, and u the n is a common factor of n plus 1 minus 2n plus n minus 1. Then we have 2n delta n. We have minus n minus 1 delta n, and minus n minus 1 delta n minus 1. Okay? And basically, look at this. We can simplify, and this will be 2 times, look at this, this will be 2 times delta n multiplied by n. Okay, what happens when I multiply a function by a delta? This is a delta, sorry, this is the value, a delta with the value of the function at that point. But the value of n at 0 is 0, so this is 2 multiplied by 0 delta n. Okay, then we have minus 0 minus 1 delta n. I take out delta n common factor here. Minus 1 of delta n minus 1. I take out delta n minus 1 common factor. And basically, this is delta n. Okay, which is what I wanted to demonstrate. Okay, so that's basically the exercise. I hope it was clear for you. If there is any doubt, please let me know, and I will try to help. Thank you for watching.